Hello everyone, I'm Sankalp Sikhat, an applications engineer at Maxim Integrated, and in this webinar today, I'm going to be talking about Maxim's wearable solutions offering and sharing the technologies and applications of our products. So let's get started. With the increase in the global healthcare costs, people are moving towards early detection and prevention, which has led to the personalization of healthcare solutions. Consumers concerned about their health are being empowered by the availability of readily available solutions that can be bought in their local electronics store or from the mainstream online retailers. For example, someone who is diabetic would like to control this condition with a convenient wearable patch that continuously measures glucose levels. As a result of all these trends, the number of wearable healthcare devices are growing. According to ID Tech X research, global wearable shipments were estimated to hit 222.9 million by 2019. By 2023, the market may grow to 302.3 million units, up from a prior estimate of 279 million. People like accessing their own health data and seeing their progress over time because the information is gathered over a period of time. So here are key Maxim wearable healthcare technology platforms that we offer at the moment. We have the best-in-class biopotential analog front ends which have ultra-low power and high sensitivity. We have best-in-class optical analog front end with the highest industry SNR. We have really good temperature contact sensors which are accurate up to 0.1 degrees Celsius, and we have efficient power management ICs which offer the lowest noise with the highest efficiency. Let's take a look at Maxim's biosensors offerings. Biosensors are widely used in health products, effectively improving our quality of life. Biosensors can be used not only in medical devices, but in health and fitness devices, in mobile devices, etc. For example, integrating sensors in the watches allows us to monitor our health status in real time and guide our exercise plan while acquiring real-time information. Maxim biosensors are divided into two main categories. The first are the biopotential sensors, which measure the weak electrical signals of the human body and record various parameters like ECG, heart rate variability, and rate of respiration. Then there are the optical sensors, which make use of the reflected light from the skin to monitor heart rate, blood oxygen saturation, breath, and blood pressure, etc. Now, moving on to ECG measurement. ECG or electrocardiography is the process of measuring electrical activity of the heart using electrodes placed on the skin. Maxim Integrated has a few analog front ends which allow you to measure ECG data, which can then be used to measure heart rate and heart rate variability. An important point to note here is that the heart rate measured by the analog front ends is typically measured using the R-to-R interval, which uses the time difference between the consecutive R peaks of the ECG waveform to estimate the heart rate. The consecutive difference between various R-to-R intervals is also used to measure heart rate variability, which is also a good indicator of your health. Maxim Integrated has a few parts in our ECG portfolio, namely Max 30001, 30003, and 30004. Max 30001 and 30003 can be used for clinical applications, whereas Max 30004 is intended for fitness applications. You can also measure respiratory rate using the bioimpedance. The bioimpedance-based measurement of the respiratory rate uses the periodic change in the resistance across the thoracic cavity to measure the respiratory rate. The periodicity in the resistance is used to measure respiratory rate as follows. When we inhale, the gaseous volume increases as the lungs expand and the rib cage expands, which leads to the increase in effective path length across the thoracic cavity. As a result, the effective impedance or resistance measured across the thoracic cavity increases. As we exhale, the gaseous volume goes down as the lung compress and the rib cage contracts, which results in the reduction in the path length across the thoracic cavity, which leads to lower resistance or impedance. This periodicity in resistance is then used to estimate or measure the respiratory rate. Max 30001 is an IC which can be used to measure ECG and bioimpedance, whereas Max 30002 can only be used to measure bioimpedance. Now, moving on to the optical measurement. Various optical analog front ends offered by Maxim Integrated make use of the light reflected back from the skin to measure the various different parameters like heart rate variability, SpO2, blood pressure, and rate of respiration. It is very commonly used to measure heart rate in various wearable sensors. Optical measurement involves shining a light into the skin and measuring the reflected light back via a photodetector. The resulted waveform looks periodic in nature because the pulsating capillaries alternatively absorb more or less light depending upon their volume, and the resulting signal is also known as PPG signal. The PPG signal is different at different wavelengths because the light absorbed by the skin at different wavelengths differs in intensity. A very important parameter measured using the optical analog front ends is called SpO2. SpO2 is the percentage of oxyhemoglobin over the total hemoglobin. It's a very important measure of an individual's health. For a healthy individual, the range of SpO2 is typically between 96 to 99%. And it can be measured using the optical front ends using the simple fact that oxyhemoglobin reflects red light more readily than the deoxyhemoglobin, but it's the opposite for infrared. So the commonly used wavelength, or the commonly used light colors for measuring SpO2 are red and infrared, and the typically used wavelength for red is 660 nanometer, and the typically used wavelength for infrared is 940 nanometers. And an important point to note is that getting the heart rate is a prerequisite for measuring SpO2. We have also tuned the performance of our sensors using independent lab testing, where we used Hypoxia Lab for validating the performance of our sensors. Nellcore N560 was used as a reference pulse oximeter device, and the sensors were calibrated accordingly. Based on the laboratory measurements, both the accuracy of Maxim's reference design made using our sensors and those of customers' designs using our sensors can meet the requirement of 3.5% accuracy by the FDA. Various different optical analog front ends are as follows. Max 30101 or 30102 can measure heart rate and SpO2, and they are intended for finger-based applications. Max 86160 or Maxim 86161 can be used for ear or finger-based applications and are capable of measuring heart rate. Max 86140 and Max 86141 can be used to measure heart rate and SpO2 and are intended for wrist or abdomen-based applications. Max 30110 or Max 30112 can be used to measure heart rate and SpO2 and are also intended for wrist and abdomen-based applications. Max 86170 can be used to measure heart rate and SpO2 and is intended for wrist-based application. Here are a few design recommendations that you can consider while designing a wearable device. Green LEDs offer more resilience to motion artifacts, therefore measuring heart rate using a green LED will give you better results. A MESA can be used to improve tissue-to-sensor coupling, thereby reducing ambient noise seeping in. A direct light path should be avoided from emitter to detector. As you can see in the figure on the top, a glass cover is used with an optical barrier, which is an example of a good design, but the figure on the bottom shows a glass cover being used without a proper optical barrier, thereby providing a direct light path from emitter to detector, which is an example of a risky design. It is advisable to use redundancy and always align photodiodes perpendicular to the wrist strap. An important point to be taken into consideration while measuring SpO2 is that the red and infrared light need the same optical path. So it is advised that the optical centers of the photodiodes be aligned rather than the geometrical centers. Here is a quick overview of Maxim's biosensors portfolio. The various biopotential analog front ends are listed below, along with the various optical analog front ends, and then there's this part, Max 86150, which offers a combination of biopotential and optical analog front end. A little bit more about Max 86150. Max 86150 is the only sensor for PPG and ECG measurements available on the market. Max 86150 has biopotential and optical channels which help to simplify the design of the wearable. And to add to the benefits, it has inbuilt ambient light cancellation and supports I2C interface. Now, moving on to body or skin temperature measurements. In addition to the biopotential analog front ends and optical analog front ends, Maxim Integrated also has several contact temperature sensors, one of the first products being Max 30205. Max 30205 contact temperature sensor accurately measures temperature and provides an over temperature alarm or interrupt output. The accuracy meets the clinical thermometry requirements specified in ASTM E1112. Max 30205 features 3 address select lines with a total of 32 available addresses. The sensor can be powered from a voltage of 2.7 volts to 3.3 volts and has a low supply current of 600 microamps and a lock protect I2C compatible interface that makes them ideal for wearable fitness and medical applications. The second part that we're going to discuss today is Max 30208. The function of Max 30208 is similar to that of Max 30205. Max 30208 can operate from a input voltage of 1.7 volts to 3.6 volts and is a low power, high accuracy digital temperature sensor with 0.1 degrees Celsius accuracy from plus 30 degrees Celsius to plus 50 degrees Celsius. The device is very suitable for IoT, medical thermometer, and wearable body temperature monitors and other such applications. Here are some design recommendations that you should follow while using a temperature sensor to measure contact temperature. It is advised that you maximize skin contact area to increase the heat capacity available from the skin and increase the perfusion rate. It is also advisable to minimize the system thermal mass by using the thinnest possible PCB or polyamide flex circuit and use the minimum amount of thermal space between contact and the temperature sensor. It is also recommended that the system losses to the environment be minimized by using the thinnest possible copper traces and having cutouts around the temperature sensor and minimizing the power and ground planes. Special attention needs to be paid to the enclosure, and it is advised that you minimize the enclosure surface area exposed directly to the room temperature air and minimize enclosure wall thickness to reduce thermal conductivity. Now, moving on to Maxim PMIC solutions for wearable devices. Power management ICs or PMICs are integrated circuits that include multiple power rails and power management functions within a single chip. PMICs are frequently used to power small battery-operated devices since the integration of multiple functions into a single chip results in more efficient use of space and system power. Functions commonly integrated into a PMIC include voltage converters, voltage calibrator, battery charger, battery fuel gauges, LED driver, real-time clocks, and so on. Maxim's PMICs include low-power PMICs and high-performance PMICs. Low-power PMICs provide the high efficiency and compact form factor needed for space-constrained applications such as wearable, hearable, sensors, and IoT devices, whereas high-performance PMICs maximize performance per watt while increasing system efficiency for computationally intensive platforms such as system-on-chips, FPGAs, and application processors. Wearable devices mainly use low-power PMICs. Wearable products generally integrate a variety of functions such as Bluetooth, NFC, various different sensors, etc. At the same time, due to the need for battery life and portability, it is necessary to achieve higher efficiency in a smaller size. So power management chips are critically important. Maxim SIMO power management chip can perfectly meet this requirement. SIMO, also known as single inductor multiple output, is the leading technology from Maxim Integrated, which allows you to have multiple power rails using just one inductor. Now, we compare the performance of traditional power management chips and SIMO power management chips. In a traditional switching regulator topology, each switching regulator needs a separate inductor for a separate power output. These inductors are large and costly, making them a disadvantage for smaller form factor devices such as wearable devices. Linear regulators are another option since they are fast, compact, and low noise, but they are very lossy, which is not good for battery life, which is a critical requirement for wearable devices. There is another option of using a hybrid of multiple LDOs with DC-DC converter, but this would result in a larger design than using LDOs alone. The SIMO architecture provides the best solution for tiny devices that require longer battery life by integrating functionality in a smaller device that would otherwise require multiple discrete components. The SIMO architecture can still maintain switching converter efficiencies while reducing the number of required inductors. We can see in the example shown in the figure, compared to the traditional power management circuit, the SIMO power circuit can improve the efficiency by 8.9%, reduce the size by 27%, and save the output current of the battery, which is exactly what the wearable device needs for its endurance and portability. Take the SIMO power management chip MAX77650 as an example, which provides three independently programmable power rails from a single inductor to minimize total solution size. A 150 mA LDO provides ripple rejection for audio and other noise-sensitive applications, especially wearable in-ear applications. A highly configurable linear charger supports a wide range of lithium-ion batteries and includes battery temperature monitoring for additional safety. Now, I would like to introduce another product, the MAX17220 family of DC-DC converters with nanopower technology. For wearable products, quiescent current is a critical current. The power supply's quiescent current is the biggest contributor to a system's standby power consumption. Lowering the quiescent current is one of the best techniques for delivering the most efficient power and the longest battery life to its designs. Consuming less than 1 microamps of quiescent current with highly efficient operation, our regulators with nanopower technology significantly reduce battery drain for longer battery life. The output voltage of this series of products is selectable using a single standard 1% resistor. MAX17220 family of parts have post-startup enabled transient protection or ETP, allowing the output to remain regulated for input voltages down to 400 millivolts depending upon the load current. The next product I would like to introduce is MAX77827. MAX77827 is a highly efficient buck boost regulator with nanopower technology targeted for one-cell lithium-ion applications, with the lowest typical quiescent current in the industry of 6 microamps. It supports input voltages of 1.8 volt to 5.5 volt and an output voltage range of 2.3 volt to 5.3 volt. The IC provides two different switching current levels to optimize external component sizing based on given load current requirements. The IC can support up to 1 amp of load current in buck mode and 900 milliamp in boost mode. Next, let's move on to today's final topic, Maxim's microcontrollers and algorithms. The first product that I would like to introduce is MAX32660 microcontroller. MAX32660 is a low-power, highly integrated microcontroller for wearable device and IoT applications. The IC combines a flexible and versatile power management unit with a powerful ARM Cortex-M4 processor with floating point unit supporting designs with complex sensor processing. The device also supports SPI, UART, I2C communication while integrating up to 256 KB of flash memory and 96 KB of RAM to accommodate user code. In addition to the above advantages, MAX32660 also has very good power consumption performance. In working mode, the current per megahertz frequency is low to 50 microamps, which can greatly extend the life of the battery. At the same time, the price of the device is also very competitive and it's under $1 per piece. MAX32660 is available in 3 different packages with a minimum size of 1.6 mm x 1.6 mm, which can greatly save the space of the circuit board, making it ideal for wearable applications. For MAX32660, we also provide the evaluation system MAX32660 EVSys to help our users get started faster. A MAX32625 Pico-based debug adapter comes with the evaluation system, which can be snap-free when the programming is complete. The debug module can be used to implement dappling functionality and features a virtual UART console. Are you designing a wearable device but don't have enough time for developing the algorithms? Then MAX32664 Sensor Hub IC is just the IC for you. MAX32664 comes with embedded firmware and world-class algorithms for wearable devices. It seamlessly enables customer-desired sensor functionality featuring a slave I2C interface for communication with the host and a master I2C interface for communication with sensors, for example, communication with Maxim's optical sensors. The IC can also deliver raw or calculated data to a processor. This is achieved while keeping overall system power consumption in check. There are 4 versions of MAX32664. MAX32664 version A supports Max 30101, Max 30102 for wearable health for finger-based applications to monitor heart rate and blood oxygen. Max 32664 version B supports Max 86140 and Max 86141 for wrist-based applications to monitor heart rate. Max 32664 version C is similar to version B, and the blood oxygen function is added to the heart rate monitoring function of the version B. Max 32664 version D is an enhanced version of version A. It can be used to monitor blood pressure in addition to the heart rate and blood oxygen and is intended for fingertip applications. Now, let us take a look at the reference designs related to these products. Maxim Integrated provides design files, firmwares, and software for these reference designs, and the collected data can also be downloaded for subsequent analysis by users to validate the end case scenario. First of all, let's talk about MaxRefTest 220. This reference design uses version A and version D of Max 32664 sensor hub that we just introduced for finger-based blood oxygen saturation, that is SpO2, and blood pressure trending measurement along with heart rate monitoring. In addition to Max 32664, this product also uses Max 30101 optical module and Max 32630 feather application platform. The product provides GUI and circuit diagrams for users, and the data can easily be collected through simple settings. Next are the head sensor platforms MaxRefTest 101 and MaxRefTest 102, which use version B and version C of Max 32664 respectively. The product is a reference design for measuring wrist-based PPG signal, heart rate, and body temperature. We provide algorithms, GUI, circuit diagrams, and a Bluetooth-based Android application for user validation. This health sensor platform integrates a PPG analog front-end sensor, a biopotential sensor, a human body temperature sensor, a microcontroller, and a power management IC along with a 6-axis accelerometer. In addition to working alone, this product can also communicate with smartphone via Bluetooth and can also be connected to a PC via USB-C cable to display real-time information and download temperature, ECG, and PPG waveforms. MaxRefTest 101 has been released and MaxRefTest 102 will be released soon. MaxRefTest 103 is the latest Maxim wrist-worn wearable device that supports heart rate variability, PPG, blood oxygen, respiration, sleep quality, and pressure level measurements. It contains Max 32664 sensor hub, Max 86141 analog front end, and a 3-axis accelerometer. We provide PC and Android software but also provide circuit diagram, firmware, and other design resources along with the reference design. Thank you all for listening. I hope this webinar was very informative to you.